All right, me and my students are really inspired about the idea of bringing artificial intelligence really pervasively into the real world, where it can interact extensively with us humans and all of the things that matter to us. Now, it turns out that the ways that we interface our systems with the real world is through sensors, and so that becomes a big focus for us. But of course, as an inhabitant of the real world, I'm really going to be okay with this only if I can be sure that these systems that are being introduced can operate robustly. That is, that they're going to work well and they're going to work safely how I expect them to. Now, it turns out what we're discovering in my lab is that in order for this to be the case, we really need a confluence of new algorithms for machine learning, new kinds of sensors that can capture very rich and textured information from the real world, and then new computing platforms that can convert those algorithms and those sensor inputs into usable actions that can be taken by our machines that are useful to us. Actually, the truth is, we're really living in a transformative time. We're starting to see machines now exhibit capabilities on the level of humans for specific tasks that we've traditionally associated with cognition. Things like vision, speech, and strategic gameplay, like I'm showing over here. Now, this has the potential to really redefine the relationship between humans and their machines. Now, the challenge is that as we've tried to move some of this capability really extensively into the real world, now, unfortunately, our machines need to deal with this extremely complicated statistics, the physics of the processes that are going on here in the real world, with human will, as I'm showing over here, and so on. And so this has posed major challenges for some of these algorithms and systems that have performed so well in the past. Now, it turns out that a major insight that's coming out of the world of machine learning is to exploit structure in data. Now, what that means is that the way that data is organized can have relevant meaning to us, not just the values that data takes. So as an example, in our work, where we're really interested in building systems that can interact with humans, one of the insights is that the ways that we interact with the physical objects around us says something about what our activities are and what our underlying intentions are. So for example, if I'm exercising, I'm going to be interacting with these dumbbells. If I'm cooking, I'm going to be interacting with those utensils. And if I'm working, I'll be sitting at a desk with my computer and with notebooks. And so one of the ideas that we've been pursuing is something that we call physically integrated sensing, where our sensors are now integrated into the objects that surround us and that we interact with, so that the sensor data is organized around these interactions. Of course, the challenge here is that we're trying to take advantage of structure from sensor data that doesn't yet exist. We're trying to take advantage of sensors themselves that don't yet exist, and then apply these to learning models that don't exist. And so for us to be able to make progress in this, what we need to do is create these virtual worlds which can allow us to emulate human behavior. And because we're constructing these, in fact, we can emulate any kind of sensor we can imagine. We can place objects here, we can place humans here, and then imagine different ways of capturing the information about them. Once we've done this, we can now start to really concretely analyze what kind of structure would be useful, what kind of sensors would introduce that structure, and then how we can build machine learning models to take advantage of that. For example, this is some analysis that looks at very simple learning models applied to physically integrated sensing, showing that we have the potential to really outperform traditional forms of sensing, say vision sensing, using today's deep learning methods. Now, once we've decided that we want to create these new kinds of sensors and we want to use these new kinds of computing models, we need to go and build all of this. As far as the sensors are concerned, a real focus for us has been a technology called large area electronics, or variously called flexible electronics. Here we can create really large but conformal, form-fitting arrays of sensors. It's really important when we introduce all of these sensors that we don't change the ways that we're going to interact with these objects. Otherwise, that structure I was so interested in will be lost. So the kinds of things we've done, for example, is create microphone arrays that are integrated in wallpaper, or gesture sensors that can detect human activities and locations, or even sensors that can be worn on humans to detect physiological signals, and so on. Now, once we have all of these distributed sensors, we also need to create computing platforms that can convert the data into useful information for our machines to respond to. Now, unfortunately, these computations really need to occur at fundamental levels of energy efficiency in these very embedded scenarios where they have very strict resource constraints on energy. It turns out, for example, that in today's computing platforms, accessing data from memory is something that can dominate over the actual compute. So we need to think about really new kinds of architectures that can overcome these bottlenecks. As an example, over here we built systems where we can actually do computation on data in memory itself to avoid some of these bottlenecks. And so this is the kind of new thinking about architectures that needs to happen for these systems to work. Now, working with students who have diverse interests and backgrounds is enormously fun. We're having great fun building the next generation of systems for the next generation of applications that don't exist yet. But if they did, they could have major impacts on our lives. Now, of course, there's a lot of pieces that have to come together here. And so the way that we attack this problem is that we go at it together. We all come in with different expertise, but we're all committed to understanding the bits and pieces that everyone else is working on so that we can create these sorts of systems that we're imagining can have this kind of impact on the world.